Hello, my name is Martin and I'm from the Karlsruhe Institute of Technology in Germany. In the next minutes, I want to present you our work on the quality control of ultrasound transducers using distribution-free overlapping coefficients. Starting with a few words where these transducers are used. Here you see a rendered image of our third generation 3D ultrasound computed tomography device for breast cancer screening. The patient lies thereby prone on top of it, and one breast at a time is immersed into this water-filled container here. The container holds 128 transducer arrays, where each array holds 18 single transducer elements, which sums up to approximately a bit more than 2,300 transducers in total. So from the imaging approach, one transducer at a time emits an unfocused ultrasound wave while all other record. Depending on the time of flight of the acoustic wave between the emitter and the receiver, we can differentiate between the transmission and the reflection signals and map those to different physiological modalities. Based on this data, we are then able to derive 3D tomographic images of the breast. And this imaging approach results in a certain set of requirements, and a special transducer array design resulted. You can see here the centerpiece of this transducer array design is a composite disc which holds 18 single PCT fibers embedded in polymer. On the front side of this disc, a matching layer is applied to match the acoustic impedance of the PCT fibers to water, and on the back side a printed circuit board is connected, which allows electrical connection and holds space for acoustic backing. The stack is then integrated into a plastic housing for protection and sealing. From the quality control point of view, two main fabrication defects have to be spotted or have to be found. These are cavities which might form directly in front or behind the PCT fibers, which on one hand would cause very low acoustic impedance matching and therefore low emission sensitivity, and on the other hand, significantly reduced functional bandwidth and high reflections, which causes artifacts in the image. The method of choice to detect those cavities or those fabrication defects would be ultrasound measurements, but they are relatively complex to perform and time-consuming, and they can only be done with finalized transducer arrays. Another measurement modality which allows the estimation of the vibration conditions of these transducers are electromechanical impedance measurements. Here you see, as an example, one transducer in two different fabrication states, so the initial state here and the final state, and as can be seen, not only for the impedance magnitude, but also for the phase, significant changes from the beginning to the end of the fabrication process can be spotted. To assess these changes now quantitatively, we derived 10 properties from each measurement. Some of them directly, such as the phase angle at resonance here, or the equivalent series and parallel resonances, some of them indirectly by first calculating the electrical input power and then deriving the effective 3 dB bandwidth at resonance or the center frequency. To now evaluate or find the best suitable property for quality control, we conducted these measurements at 5 fabrication states or instances throughout the course of the assembly. The first is the initial state, which can also act as an incoming inspection to sort out good from bad transducers. The second state is when the PCB was added on the backside. This induces additional parasitics due to the parasitic capacitances of the PCBs. And the next state, when on the front side, the matching layer is added. Then when on the back side, the backing material is applied, which is filled into the designated holes here in the PCB. And then in the final state, which adds additional parasitics to the electromechanical resonator, as we need to connect the transducers using a connecting board. So just as a quick reminder here, These are the two fabrication states which are of main interest for our quality control metric. To derive now a suitable property, we conducted an experiment where we measured 144 transducers, which corresponds to 8 full transducer arrays. Here you see as an example the relative distribution of one property in form of a histogram of the electrical input power, so the 3 dB bandwidth of it. As we can see here, some variations in the spread of the distribution can be seen, as well as overall significant rise of this bandwidth can be spotted. In order to classify this rise now and to be able to group them in before the backing was applied and after, we have to apply some statistics. Unfortunately, most of our transducers did not comply well with normal distribution behavior. So some errors would be inevitable when using only mean and standard deviation procedures. Another way to characterize and assess these two distributions are using an overlapping coefficients, which can be calculated by estimating from each histogram or from each distribution a probability density function. This density function is calculated using a normal kernel. The intersection point of these estimated probability density functions can then be used as a one-dimensional classifier to evaluate. So it's more likely now to be in the fabrication state where the matching layer was added or after the backing was applied. And it also allows us to estimate the probability of false negative decisions, which would be in this case here that the backing is not connected but detected, and also false positive decision means that the backing was connected but actually not detected. Using this metric now allowed us to evaluate all the derived properties throughout the course of the assembly to find the best suitable property. Here you see the results matrix, where on the x-axis we see the 5 fabrication states, on the y-axis the 10 electromechanical impedance properties, and color-coded the respective overlapping index between the current and the preceding fabrication state. Very low overlapping, so very blue values mean that a high separability between the two groups or probability density functions is given, and very high overlapping means very low separability of the respective groups. For us, best suitable property would be one which shows very high overlapping for adding just additional parasitics, as happened here in the second fabrication state or in the final state, because this means it exhibits low sensitivity to adding parasitics and so varying measurement conditions, but very high sensitivity when one of the sides of the PCT fiber is connected. So very low factors for that, which exhibits good separability. Analyzing now several of these properties shows that, for example, the resonance frequencies would be partly suited because some parts are blue, some parts are yellow. But when analyzing all of the properties, the best suited property seems to be the bandwidth of the electrical input power, as it complies exactly with the requirements just stated. Looking at the scatter plot of this property here reinforces this suspicion, as when can be seen the distribution of the initial state and the PCB state show a very high overlapping, then a significant rise when the first side of the PCT fiber is connected takes place, and an additional rise after the second side of the PCT fiber, so after the backing is applied. Also, adding the final state increases the variability, but also shows and exhibits high overlapping. Deriving now the intersection points and overlapping, based on the overlapping calculations, we see that 2 one-dimensional classifier can be applied here, which would allow to rate final transducers now if the probability is very high that none of the sides of the PCT fiber is connected or only one side is connected. And also, if only one side is connected, exhibits a very low false negative probability of lower than 1%. So it seems like a reliable classification using this property is possible. This brings me then to my final slide. I hope I could convince you that quality control of ultrasound transducers is possible by easy to perform electromechanical impedance measurements. The presented method using the overlapping index based on individually estimated probability density functions needs no distributional assumptions. So it relies entirely on the measured quantities. This, on the other hand, bears the necessity to be really sure that the measured samples are representative for the population. In our case, the bandwidth of the electrical input power was found the most sensitive and specific property for quality control, or for one-dimensional quality control. It allowed us now to assess the quality of the fabricated transducer arrays to be now used in our 3D ultrasound computed tomograph for breast cancer screening. With this, I want to conclude my talk and thank you very much for your attention.